let's combine the first and second laws of thermodynamics to get the combined first and second law. So the first law of thermodynamics is that du is equal to dq plus dw. The second law of thermodynamics says that dq, or ds, is greater than or equal to dq over t, where the equal sign is associated with a reversible process, and the greater than sign is associated with an irreversible process. And we said in class on Friday this will associate as a real process, something that really occurs. So let's multiply, let's take this second law here, multiply both sides by t. So t ds greater than or equal to dq, or dq is less than or equal to t ds. Let's take the first law and rewrite that as du minus dq plus, sorry, it should be a minus dw. That's equal to 0. Now let's use this relation here, dq, and replace that with tds. So du minus tds minus dw. Now dq is less than tds, or tds is greater than dq, but this is entering as a minus sign, so you're subtracting off a bigger number. So initially it's 0. If that is equal, this would be 0. But you're subtracting off a bigger number, so that will actually be less than 0. So less than or equal to 0. This is the combined first and second laws of thermodynamics. Now let's assume that we can only do PV work. So in that case, the combined first and second laws of thermodynamics is du minus TdS minus PdV is less than or equal to 0, where the equal is for reversible processes and less than is for irreversible processes. Or we'll just write this, du minus TdS plus PdV is less than or equal to 0. Now we're going to say, all right, du at constant s, so ds is 0, and at constant v, dv is 0, is less than 0. So this, or less than or equal to 0, but let's make it a real process, so less than 0. So this is a criterion for, and again, this is the internal energy, the energy of the system. This is a criterion for spontaneity, for constant entropy and constant volume. So you have some process that occurs at constant entropy and volume. You just look at the change in internal energy. If it's less than 0, it's spontaneous. So that's where this comes from. Let's look at this equation. There's a constant P and S. So we'll start with the definition of enthalpy. H is defined as U plus PV. That's how we defined enthalpy. Okay, let's take the differential of H. dH is du plus PdV plus VdP. Let's rearrange this to say that du is dH minus PdV minus VdP. And we've shown that we can rewrite this equation here as du is less than or equal to TdS minus PdV. In other words, take this term and this term, put it over here. So that's what du is equal to. So we can say that that is less than or equal to, for reversible processes, TdS minus PdV. Solving this equation for dH is, well, actually, let's take these things and put them over there. So dH minus PdV minus VdP, put that minus TdS plus PdV is less than 0. Let's get rid of the equal, so we'll look at real processes. And how convenient, the PdV cancels out. So we're left with dH minus TdS minus VdP is less than or 0 for a spontaneous process. So this is a criterion for spontaneity for constant S and P. Constant S, constant P, dH is less than 0. dH at constant S and P. So there's where that comes dH at constant S and P is less than 0.